Uh, well, we had some little delay. Welcome everybody to this new edition of the Chem Seminar Series, Spring 2025. We're excited to have you join us today. And today is our pleasure to introduce Professor Gabor Orosz. He's a professor of mechanical engineering, a professor of civil and environmental engineering at the University of Michigan, Ann Arbor. He earned a master's degree in engineering physics from the Budapest University of Technology in 2002 and a doctorate in engineering mathematics from the University of Bristol in 2006. His current research focuses on nonlinear dynamics and control, time delay systems, machine learning, and data-driven systems, with applications to connected and automated vehicles, traffic flow, and biological networks. So please join me in welcoming Professor Gabor Orosz.
Thank you very much. And so I'm happy to be here. This is my first time at UIUC. So I enjoyed a lot the visit. I met with a lot of people, including the students here just before the talk. And was really impressed by the breadth and the depth of the research you guys are doing here related to transportation in general. So today I try to tell a little bit about my journey through this field since I joined the University of Michigan. And of course, it's not going to be a complete story for every detail, but hopefully I give you some idea what my group has been working on in the last couple of years at least. So I think I need to say, okay. Somehow. All right. So let me start with this one. There were a lot of questions before the talk, if you go and become a faculty somewhere, what's going to be your future? So here are a couple of examples. So these are the people whose research is I'm mostly going to talk about today. And then they kind of graduated from my group quite recently, I would say. So Tamás is a professor now at Wichita State University. After he worked with me as a postdoc, he actually did another postdoc at Caltech with AeroNames. And then he actually now works much more on robotics rather than transportation system, but we still have some collaborations on transportation. And Charles is the faculty in University of Buffalo in mechanical engineering. He also shifted a little bit his research topic. He's still keeping some of the connected vehicle research, but he works also on robotics topics. And Sergey actually moved to industry. So he is leading now a group in Toyota Info Tech Center in the Bay Area. And he mostly focusing on V2V connectivity and V2I connectivity. And Anil recently graduated. He's actually a postdoc now. He went to Europe, worked with Bart Scooter in University of Delft. Okay, so you can see that there is quite a variety of different careers people can build up. Some become faculty, some become industry experts. But there's a lot of opportunities ahead of you once you graduate. Okay. And just as a motivation, I would like to first show you what kind of vehicles we have been playing with. So when I got to the University of Michigan, of course, I was a young assistant professor. When I was thinking about experiments, this was typically what I was imagining, right? So these robots actually we built, and they are connected and automated vehicles back maybe 10 years ago. And of course, we designed everything. We designed the connectivity. We designed the controllers. And we kind of expected them that they behave the way we want them to behave. Okay, so this is where we started. And then as kind of M-City opened their gates, we had the opportunity to play with real vehicles like this Kia, which my group basically built. I mean, the car was built by Kia, right? We just did the software part and the control. And then eventually I worked with a company, Navistar, which actually had a manufacturing facility here close to you in Chicago. And then you can see at that time, the truck was so big that it was even bigger than my whole group, right? So it kind of was an interesting journey. I'm going to skip this one because of the interest of time. But let me show you like one of the simple experiments we have been doing at the beginning. So in this case, we wanted to control these vehicles. I'm only showing two of them for you. And then as we kind of said, well, can we build something, a car following rules, right? So those of you who work on transportation modeling, they know that there are many ways we can model human drivers, and we already spent quite a bit of that. So can we kind of bring that knowledge over and build controllers for automated vehicles, okay? And the key idea is, and now it's basically, this is built in every ACC algorithm on a vehicle you buy, is that you set your speed, right? And you set your distance, but you don't set it in terms of meters, you set it in terms of time headway. You want to follow that other vehicle. And you basically make this as your control objective, right? So I want to be close to this function. And then you can build a controller like the one I'm showing you here on the bottom, which is basically saying, I want to match the velocity of the vehicle in front of me. This is the second term here, right? And at the same time, I also want to kind of get close to this range policy, and that is given by the first time. And when we were running it on the robots, actually, they did pretty well. The choppiness is because we going through Zoom and everything, right? Otherwise, it's a pretty smooth video. You could see actually we used a range sensor. There was a laser sensor. So there was a, oops. Yeah, there was here a signal, which is kind of bouncing back, and this is how we measure the distance. And actually, we were able to reproduce this behavior really nicely in the lab, okay? So once we kind of went to MCity, we were like, wow, okay, we can do it with real cars now, okay? So this is one of the tests we were running. So this is what we call the grand circle of MCity. It's not as grand circle as you guys have here in your test track, but it allowed us to kind of test these algorithms. And now in this case, the car which is running behind us is trying to follow this rule. It's already using V2X connectivity. And as you can see, we're doing different maneuvers. We're slowing down, we're accelerating, sometimes just driving constant speed. I wanted to make sure that, number one, we're staying safe, right? And number two, we are also efficient, okay? So these two things, safety and efficiency, were the two key metrics which we have been going after. And of course, sometimes they contradict with each other. I will show some examples for that, okay? I also found that V2X connectivity is very useful. As a matter of fact, the test you have seen, we didn't have to use sensors. We simply used connectivity. We calculated the distance between the vehicles, and it was very convenient. One additional benefit was, if we wanted to run this test again with exactly the same behavior of the front vehicle, we just played it back. Okay, that was very useful because we could separate whether a certain behavior is because of the variety of the behavior of the vehicle ahead of us, or simply the controller, is performing different in every round, right? So if we play back the same signal, then we could actually follow vehicles which were not even there, right? And we could test our controllers. And as you can see, in this case, this was a very relaxing test. The driver was so relaxed, he put out his hand on the window and was just gliding through the evening drive. Okay? So indeed, as I mentioned, these algorithms are already on vehicles, so production vehicles. Actually, there are people who try to backward engineer them. For example, one of your former colleagues, Dan Burke, did some work on that when they took some vehicles which were already production vehicles with ACCs, and they try to figure out what is that algorithm, right? In our case, we had the luxury that we built our own algorithm, right? And we could play with it and do whatever we wanted because the cars were hacked. So how could we go further than this, and why this connectivity is useful for us? So let me show you probably the simplest non-trivial example where it starts to play a role. Okay, so clearly the previous example, you could argue that, well, connectivity is maybe not so necessary. You could get it from camera, you could get it from LiDAR and so on. But the configuration I'm showing here, if you are sitting in this blue CAV, then you will not have access to the signals of this CHV unless you have connectivity, okay? You will only see this red vehicle and only respond to that, okay? But if you have connectivity, then you are actually able to add this term to your controller, and this is the kind of the simplest representation you can imagine, where you say, I also want to respond to the velocity of this black vehicle, which is a through vehicle ahead. Otherwise, the controller is the same as before, okay? And what we did, we basically built up the mathematics behind how to design these controllers, okay? We used something called transfer functions to represent the link between the vehicles. And then we could actually represent the head-to-tail response. So basically, we could sum up how this blue vehicle responds to the black vehicle directly through this connectivity, and how it responds to the black vehicle because it propagates from black to red to red to blue. Okay? So that's basically what this simple formula is saying here. And we found that if we make this always smaller than 1, then actually can help us to attenuate these perturbations traveling on the chain, okay? So the way it worked is that we kind of played in these gain parameters, this beta 01 and beta 02. So again, the beta 01 is how much I respond to the velocity of the vehicle right ahead of me. And the beta 02 is how do I respond to the velocity of the black vehicle. And so what you see here is that actually if we don't have connectivity, then we can make things better, right? Because the human is kind of not doing well here. So it's already mixed traffic, right? We have humans in the loop. But then the blue vehicle is doing better than the red one, but it's still above 1. Okay, so we are not satisfying our design perspective. But once you turn on the connectivity, you can actually push down this transfer function. And it always becomes less than 1. And then this means that actually through the connectivity, I can make this unit, this 3-vehicle unit, is a nicely behaved unit in traffic, okay? Because from the head to the tail, I can attenuate these waves, okay? And I will show you why they are so useful. Our original kind of motivation was like decaying traffic jams, right? And that was kind of the jam mitigation idea we had, but I will show you that it will have other benefits in our case. So let me show you how does it work in experiments. So this is one of the experiments we run in M-City. You see 3 vehicles following each other. And you see that they are kind of having this braking pattern. And now the white vehicle, which was what we built, actually was doing a very harsh braking. This was done by a human driver. And at that time, Sergey was in my group. So he's the guy who works at Toyota now. He's also a race car driver. Okay, so it's really nice to have a safety driver who could really make sure that, you know, in these experiments we stay safe. But what you see here, in particular in the acceleration, there is a harsh deceleration of the first vehicle. That's about half G, okay? And it gets worse and worse. And for the blue vehicle, which is the last one on the chain, it's 1G. So what does 1G means? Your entire weight at the safety valve, okay? I can tell you that hurts. Okay, especially when you do it multiple times a day, this was a painful task with the human. Okay, so then the question first we were asking, like, what if we change this blue vehicle first just an automated vehicle, no connectivity? It's just what basically in those days what the industry was pushing for, because as you know, so this experiment is back in 2017. As you know, by now none of us are driving. And all of our cars are automated, and we don't even have to worry about mixed traffic and any of these things, right? And if you talk to people in 2017, you often heard this narrative, right? Well, that didn't really happen actually, but we still checked, you know, what can an automated vehicle do, okay? And it does better. So the video doesn't really show it very well, but when you look at the signal, actually you can see something similar happening at the beginning. So there's a harsh braking on the first vehicle, the next one is doing harsher, but now the automated vehicle goes down to just half G, okay? That's much better. That actually means that you can, but it's still a harsh braking, but you know, you can bear it, I should say. So this is how far you can get with automation. Once we added connectivity, and this is what the situation I was explaining with those mathematical designs, basically we went down to a quarter G. Okay, so what quarter G means that if you have a cup of coffee in your hand and this car is driving, then you're not going to spill it. Okay, my students love this test. Well, I was drinking the coffee, but you know, of course, it didn't hurt them, right? So this was really nice. And we kind of started to see that all these kind of theoretical construction, when we were thinking about, you know, mitigating those congestion waves traveling on the chain, actually have very tangible safety benefits, right? Because you went from 1G to half G with automation, which is an expensive technology compared to connectivity. And then adding connectivity, we went down to a quarter G, okay, which made it a very nice experiment at the end. So then we got kind of excited. And we found this fantastic test facility at the state of Michigan, okay? They didn't know we were testing there, but this is a road between Howell and Mason. And the nice thing about it is it has a section which is about 8.5 miles long, and it's uninterrupted driving, okay? So basically, you don't have anywhere where you have to give the way to other vehicles. You can just drive, okay? So we created our little traffic here with these 8 vehicles, and we were driving it up and down on this road, and we were testing these controllers, okay? So we were playing, of course, by that time, we already know how the gates should be tuned. We did it on the test track, right? But here we were playing like what kind of connectivity we want to consider in the system, okay? And then, of course, the main question of the students every day was, who's gonna drive the Dodge Challenger? Okay, so that's kind of the major thing, okay? So let's see how did it go. So this is one of our tests. In this case, actually, all the vehicles are human-driven, right? So we collected all the data, and we had still the connectivity turned on, but we are not using neither connectivity nor automation, okay? And what you see here on the top is that the blue vehicle, which is at the front, is doing this kind of traffic oscillations, right? In this case, the driver, which was me, was kind of trying to trigger these waves propagating along the chain. And as they propagate along the chain, and by the time they reach the blue vehicle, they indeed become much stronger, okay? And that's because we humans are actually quite string unstable. We have the tendency to actually increase these perturbations, primarily due to our reaction time, okay? So our reaction time is about 1 second. Sergey could, it includes yours and the cars, right? So my student Sergey could go to like 0.8 seconds. That was actually the best in the group, right? Some students who were not paying attention could go to 2 seconds sometimes, right? In this test, we didn't allow them to drive. Anyway, so that's the main reason why these perturbations kind of get amplified. And then I'm zooming here, one of these, right? So you see how they propagate along the chain of vehicles. And indeed, the blue vehicle is doing pretty bad in this case, okay? And then one other consequence of this was that if you go along the chain of vehicles, the energy consumption is getting higher and higher and higher, okay? We calculated the energy consumption per unit mass because we could compare, in that case, different vehicles. And we only calculated from the kinematics, okay? So we didn't really measure the actual fuel economy of those vehicles. But it was very clear that as you go down on the chain from brown to blue and pink, this is increasing tremendously, right? So in this case, if you compare, actually the vehicle at the end of the chain is eating about 1.5 times more fuel than the one at the beginning of the chain, okay? So indeed, this is only true for this particular experiment. It's not true in general in traffic, but it worked pretty well in this case, okay? So we could see this happening. And then what we did was we started to add automation and connectivity. Once we added automation, the situation already started to get better, right? So these perturbations between the brown and the blue is much less amplification. You can see it also here. And also the energy kind of started to climb down on the ladder, okay? So this was working pretty nice in the test. And then once we started to add connectivity, then we started to see additional benefits, okay? So of course, every test is different here, but we could also see, the relative position of this blue vehicle in terms of energy consumption. And this was kind of when we were playing like which vehicle we are talking with, because in reality, you may not know whether you're talking to the black or the green vehicle. So it was running the same controller. And eventually kind of this was the most complex scenario. And this was also the most beneficial, right? So we have connectivity here. You can argue that in this case, we have penetration rate of 50% connectivity and 12.5% of automation, right? I mean, of course, you have to kind of consider these with care, okay? But the bottom line was that we started to see these benefits and we really got excited about it. Now, this was one set of experiments. So we later started to do more analysis and more simulations to really understand whether these benefits can be retained for other different scenarios, okay? But just to show you, one nice thing here is what we noticed is that basically if you compare the automation only, which is the top figure, and the kind of the most connected situation, which is at the bottom, the blue vehicle is saving 19% energy just by the connectivity, okay? Because it's responding to those perturbations in a proactive manner. And interestingly, even the vehicle behind was saving 7% energy. Okay, so if you drive after let's say a fancy level 4 automated car and it's designed well, maybe you can also save some energy, right? Because it's kind of doing a nice and smooth motion. So it actually can impact the traffic behind, okay? And we found it really nice and interesting. So then we're going to skip this. We start to look at these different penetration rates, okay? And then simulation-wise, we start to kind of compare what happens. So the top is showing this is simulation where it's only humans. You can see these amplifications as we go along the chain. And as we kind of start to put in these connected and automated vehicles with higher and higher penetration, they start to break down these congestion waves, okay? So that's kind of the trick here is indeed that they don't just have a smart algorithm, but they also kind of look ahead and they understand what kind of waves is gonna hit with them. We even try that, for example, when the other vehicle is really far, sometimes it's good to put in some delay so they respond at the right time when the wave hits them, okay? It's a little bit like how you surf. If any of you surfed, though I know, I'm not sure in Illinois there are that many opportunities, but if any of you go to well, actually Lake Michigan, some people are surfing, right? So you have to kind of start to pedal at the right time and act the right way to catch the wave, okay? So this is kind of the idea why sometimes we even add delays into the system, even though typically those are bad for us. And then as you can see, as we increase the penetration, they are actually breaking down these congestion waves better and better. And it turns out that this is working much better compared to if you only use automation. Okay, so already if you have like 30% of penetrations, basically we completely destroy these congestion waves. We found that if you have automation, then you typically need much higher percentages. These are simulations and we are looking at the worst case scenario here. So that's why actually these numbers are so high. Okay, I'm gonna skip this part, it's a little too much analysis, but I wanna mention this because this is kind of closer to you guys. So as I mentioned, we also worked with this company, Navistar. After, the way it worked is basically they came to our test track and we showed those initial tests, right? Which I showed you, we went from 1G to half G to quarter G. And they really liked it, but they told us that, Gabor, we have a much bigger problem. And then they showed us this guy, okay? So why is it a much bigger problem? Well, it's a very good picture. There is a Dodge Charger in the back, okay? That's a standard American muscle car. So this, of course, is still an internal combustion engine, 400 horsepower, okay? And the weight of the vehicle is about 2 tons. The truck at the front, it also has a 400 horsepower engine. And the weight of this truck on its own is 9 tons, okay? And it's supposed to pull another 21 tons, okay? So you could see that the power to mass ratio is much, much worse in case of the truck compared to this vehicle, okay? It has much more lags in its dynamics. It has larger delays. So it turned out to be much more challenging to control it, okay? And of course, Navistar was primarily interested in trying to do some testing in terms of fuel economy, okay? So basically the 3 things we wanted to achieve, one is safety, okay? And for that, we use a technique called control barrier functions. The second one, we wanted to respond to elevation. Okay, these guys going up and down, it really matters when they accelerate and when they decelerate. Okay, and finally, they don't do it on their own. They do it in interaction with traffic. And actually, this was the question which Navistar was interested in. They already had a technology which was responding to the elevation. And they even had the technology which was a standard ACC responding to the vehicle in front. But they couldn't put the 2 technologies together, right? Because they didn't quite understand they were different logics, right? And they had all like, oh, maybe when it's really close, then we should switch from one to the other. When we're really far, then it turned out that, you know, it burned all the energy they could save with the energy saver, right? In some other cases, oh, maybe we changed another way, then it became unsafe. So this was really the challenge which they came to us, is like, we already have these 2 technologies, put it together, right? It sounds very simple, but actually it was much harder than we originally thought. So this is one of the early tests which we are running. So this is in South Bend, Indiana. As you can see, this test track belonged to Studebaker about 100 years ago. That's why the trees here are writing Studebaker here. Okay, that's a car, doesn't exist. It only existed in the 1930s. And this is their durability track. You could see our elevation went from 190 meters to 130. And we also have to impose some speed limits, right? Because we want to keep the safety. So when, for example, we run our optimization for fuel economy, first thing was that the theoretical results were not matching the experimental ones, right? So it's always the case that you will have a gap between it. But in general, it kind of worked pretty well. So this is one of the tests we were running when we were only responding to the elevation. Okay, so as you will see here, the truck will start, we speed it up twice, so we're not going this fast. And then now the truck speed is kind of trying to follow the dashed line, which is coming from that optimization based on the elevation. Okay, and with this, we were able to save quite some energy compared to some traditional driving. Okay. We also compared what happens when we follow another vehicle. So we basically took a car in front of us and we said, okay, we want you to run this in this amount of time. And then we assigned, how it goes. So in this case, that also worked very well. Okay, so this was this technology. Honestly, we had to recreate both of the technologies, what they had, rather than just using the two things and plug them together. But you see here, as the leader is kind of going ahead of us, now we are in this ACC mode. And every time we kind of step on the brake and also accelerate as the other vehicle is kind of moving ahead of us, okay? And interestingly, you can see these kind of stairs as we accelerate. Do you know what is that? Why do we have those stairs there in the red signal?
Maybe because the truck has more gears.
Exactly. So trucks has more gears actually. And what happens is that they, even lose speed when they change gears, right? So that was one of the kind of things. And what you see here is when we integrated the two technologies using this technique called control barrier functions, then we only intervene when it was necessary. So we follow this other vehicle, we follow the assigned speed when it's necessary. And when the vehicle in front of us is stepping on the brake, then we are going to brake, but only as much as necessary to maintain the safety. Okay, so this was actually something very nice. And I show you how kind of close we could get to the ideal situation. Okay, so you see that on the top right, the green one is when we only respond to the elevation. Okay, compared to that, the red one was doing about 25% worse, right? Because we always follow that other vehicle. Even if that vehicle is accelerating uphill, we keep going after that, right? Because our ACC is studying that. But using this technique, we are actually coming down pretty close to the energy optimal. And then, this is how far we were able to get close to it, right? So we could actually save about 20% of the energy. We couldn't save all the 25, which is kind of the theoretical limit, but we could save 20% of the energy, okay? So then the company said, yeah, this is a test track, right? You can do that. So what about we push you guys out on the real road, okay? So when we went out to Kentucky, okay? So first of all, they had great food down there in Knoxville. I never ate that much biscuit in my life, and we were on that trip. And this was typically driven by Robbie, our driver. He was an expert also in biscuits, okay? So we found this section of the road, which is about 15, 16 kilometers long. And you can see there is severe elevations there. So this is kind of the end of the Appalachian Mountains, and you can see kind of go up and down. You can see Arnold and Chargers in the, and you can see also it was during COVID time. So almost everyone were wearing masks all the time. And so this is how these tests look like. So when we were only running the energy efficient controller, it was trying to follow this predetermined signal. It was doing relatively well. But then we also did some tests when we asked the other vehicle in front of us to sometimes up and down, slow down and accelerate, okay? And we did ask the other vehicle to do nasty things for the truck. For example, accelerating uphill, okay? When the truck did that, it was burning a lot of fuel. But if you are running in ACC, this is what's going to happen, right? So this was kind of the main idea in this case. And then, so this is how the experiment looked like. In the first case, I will show you that how this was a real road, right? We couldn't control the traffic around us. We need to make sure that we are safe all the time. So in this case, we are following our vehicle, which is also connected. We are detecting it to the radar. We are also getting the connectivity signal. But now we got a cut in, and we had to respond to that, right? That vehicle we didn't control, and luckily, the algorithm worked fine, okay? So it took some tuning, but at the end of the day, we were safe. And maybe in terms of energy, this was one of the most interesting things. So we are following another vehicle. We're running basically the energy optimal, okay? But then at some point, we're going to catch up with other vehicle, okay? And so you will see that soon. Now we turn on the safety critical system. So now we are doing basically this CCC. And then we're just following that other car because that's kind of also good for us in terms of energy. And at some point, that other vehicle is going to step on the gas, and then we let it go, okay? And this all happens automatically. Obviously, the logic was not kind of figured out by hand, but this is what the CVF basically doing. So you can see this maneuver here. We are slowing down, we're catching up. Eventually, we are letting it go, and we're just going with that speed, which is designed for us. So we spent 2 weeks in Kentucky. It was really fun to work down there. And we learned a lot, what is possible, say, in theory, what is possible to do on the test track and how we can actually transfer it into a real system on a real highway. So I just want to finish with this video, okay? This is going to tell you why we are actually doing this research. So I think this is from the third installment of Mission Impossible, right? So this guy probably look a little familiar for you. He's now running I think the 8th one is coming out. So we'll see what's going to happen. But the third one was the best because he was actually, his decoy was that he was a transportation engineer, okay? So he's going to explain to you how traffic works, and hopefully you will like it. Wait a minute. Not having any sound. Do you think we can have that?
Yeah, we have it silent here. You turn on yours.
It's working? Are you sure? I don't think so. There is no sound. Well, let me just play the video, and then you guys will not hear the sound. I'm sorry about it. It's too complicated, so I prefer not to do this internet stuff in general because it's always yeah, share the sound, so it's not because of that. Yeah. Okay. I would change that, yeah, which is this one, right?
The presentation, yeah.
I try this. Okay. Well, this is the best we can do, okay? No, it's worse. Okay, I will skip that. I'm sorry. You can Google that. But anyway, maybe the last thing is if you're interested in more, there's an upcoming book which is containing much more information about these theories and experiments. So with that, thank you very much for your attention, and I'm happy to answer any questions.
We'll start taking questions from the room, in case anybody has one. Professor Yan.
Yeah, thank you, Dr. Orosz. Very nice presentation. Just a little bit clarification. Maybe you mentioned that, but I missed. Your earlier part about the string stability, and then you actually had a nonlinear model, right? Where you have this bounds, physical bounds on the
Yes.
speed. How do you deal with that while you're linearizing it?
That's a very good question. So in what I showed today, this was linearization, and that allows us to use these transfer function techniques and so on. We also looked at the nonlinear level, and the tricky part with that is that sometimes the linear analysis doesn't work. Okay, so let me show you one figure on this, which is probably explaining it well. Yep, so hopefully this is it. So what happens is that on the top, I'm actually showing a simulation where I'm comparing stable and unstable. And this is what we're kind of talking about today, either an amplification or there is a decay. However, for some parameters, what we find is that we can actually see both for exactly the same parameter. So at the bottom, I'm showing exactly the same system on the left and on the right. Same cars, same humans, in this case, same parameters. The only difference is that the perturbation at the beginning is a little bigger on the right, okay? And what happens is that in this case on the left, you see a system goes back to equilibrium, so it looks stable. But on the right, it actually looks unstable. It is unstable. So there is this bistability, which is really coming from the nonlinearities in the system. And in this case, of course, if you linearize, you're not going to see it, right? You're always going to see that the system is actually stable because according to the linear analysis, it will be still stable. So in this case, we used what we call bifurcation analysis. So we actually put the system on a ring because that's a little easier to analyze. So we don't have to think about what kind of perturbations we are doing. And then we basically figured out what is the underlying thing happening in it. It turns out there is an unstable motion in it, which is giving us a threshold. If we step on the brake less than that unstable oscillation, then we're going to return back. And if we step on that thing more, then we're going to see the jams. And so we have a version of these controllers when we take this into account, and then we design the parameters such that the system is not bistable. So we basically can stabilize it. But indeed, it does require more kind of mathematics to be able to do it at the nonlinear level than we could do it on the linear level. Sure.
Thank you for the nice presentation, Professor. I was following your experiment where you had those 8 cars following each other, and I was interested that whenever you're connected to more vehicles, then you seem to be doing well in terms of even better in terms of like avoiding the harsh brakes and stuff like that. But I was thinking maybe there is a threshold, right? Maybe if you're connected to 5 more cars, then you don't get any benefit. Have you tested?
Yes, we tested it with simulation. So on we were limited in terms of time when we were running these tests, so we couldn't check all the configurations. There was another limitation. At that time, we were using a technology called DSRC, and the range was roughly that we could reach 4 cars. So if we had more, then would sometimes break down. But in simulations, we were testing, and you're absolutely right. So eventually this saturates, right? So if you add more cars, at some point, you're not going to see much more benefits. That's one thing. The second thing we found, and this was also interesting, if you go really far, it's really a good idea to add a little bit of delay into that, how you respond to that vehicle, right? Because imagine if you have a car 20 cars ahead, slams on the brake, and you suddenly start to slam on the brake, that would be really weird, right? So in some sense, there is also another optimization when I'm going to respond and not just who I'm going to respond. But you're absolutely right. There is a saturation here. You won't be able to get too much benefits as you go much. I mean, the benefits become not so significant. They vanish basically.
I realized that this research is basically following a car, right?
Yeah.
But because you are very interested in energy savings as well, why don't you consider, because you already have this connectivity, why don't you consider passing over, right? Like instead of like braking, if it's a more...
Absolutely. So Indeed, in this case, we restricted ourselves to a single chain, and then this is where we're at. And you're right, in many cases, it actually makes sense to just go to the other lane. So we tested that situation a little bit, mainly in simulations. In one of the tests, what we were doing is that we had about 5 vehicles driving in traffic, and we had all the data. And then what we were doing is that basically we're getting multiple signals, right? And they were from different lanes. So what we did was we kind of figured out which lane is the most energy efficient, and then we kept moving between the lanes. And we indeed could get a lot of energy benefits by that. Of course, we also wanted to limit, we didn't do that jump like every 1 second. So it was limited how frequently we made the switch. And we were playing with that, but certainly that can help you a lot, right? So if you want to move through traffic and you have a bad lane, good thing is to move to the other lane. But we never get it tested in real traffic, to be honest. You could, because the main thing is that the less you respond is the better for you, right? So in a truck, when you step on the brake and then you has to accelerate, that's an issue. There was one interesting thing I wanted to mention about the 25%. So when we were showing it to Navistar, they didn't want to believe it. And one of the drivers said, he was actually a professional driver. He had the commercial driving license. And he said, I can do better than this. And we were like, okay, fine. We run the same thing, the car in front of him, right? The time was set, right? That car always did this in 3 minutes or 10 minutes or whatever the lap time was, right, to the second. I said, just drive after it. And actually, when you were sitting next to him, felt good and things like that. And then we showed him the data and said, look, Dean, so this is what, the nominal thing is if there was no car in front of you, okay? Then this is what, our system is doing. This is what the ACC would do. And this is what you did, right? So when he started to see his own data was much worse than even the ACC, and he was thinking he was driving so nicely. Because of course he had zero foresight, right? And he was always just responding to that other vehicle. So it was interesting to see how much, what he felt and what was the data was actually different from each other.
Okay.
Sure.
When you say connected, and well, it could be different in the different experiments. What connection do you establish, and what's the minimum information that is shared? Like,
yeah.
How is the connection established, and what is it that you share?
So this was commercial technology. Most of the experiments, it was what we call DSRC, and then other experiments were the newer technology called CV2X. But to really, these are just the name of the technologies, right? What we really exchanged was basically GPS position, speed, and heading, right? And those are in what we call the basic safety messages, which are by default are sent by these devices. Actually, you can send more information. You can send acceleration if you want. You can even send state of the vehicle. You could even send your intent. Like if you are an automated vehicle, you can send your plan to the other vehicle. This is one interesting research now that like how could we use that to actually benefit, because then you start to see more horizon arising in the system. So, but in these experiments, these were these basic information. Okay, so
and how is the connection to what signal?
So this is a technology which is 5.9 gigahertz carrying frequency. And it's basically, a first technology was Wi-Fi based. So imagine like the Wi-Fi we have in the room, just in different frequencies. The next technology is cellular based, but it doesn't use the cell tower. So it's direct vehicle to vehicle, basically. And the protocol is what we call broadcast and catch. So everyone is talking, and whoever can listen is listen, right? That was kind of the main idea. So we didn't have to establish a channel. To be honest, it was harder to do with the robots. In case of the robots, we hacked the Wi-Fi of the tablets. So we basically built our own Wi-Fi network with their Wi-Fi. In this case, this was basically almost plug and play, right? I mean, of course, we had to work with a company who was giving us the devices, but they had a lot of help in that. So yeah, hope that answers the question.
I'm gonna take one last question before the end of the session.
Sure.
Thank you, Professor, for the presentation. Maybe I'm wrong, but I noticed something in the video of the truck following the vehicle in the highway,
Mhm.
that I noticed that at some points, the truck followed the wonder of the vehicle that was ahead. Maybe I am wrong. So I wanted to ask you if there is some control in this, not only longitudinal direction, but also in the transversal direction.
So
Maybe if for some reason the vehicle ahead cannot keep the lane, I don't know.
yeah, that's a good point. So in this case, whenever we drove on public roads, the steering was always humans, right? It's just because, you know, our goal was not to design the next level for AV. Our goal was to test these algorithms, right? So it could be just, you know, Robbie was doing something at that point. We also played a little bit, however, with lane keeping algorithms, and connectivity was also useful for that, in particular in inclement weather. So we had experiments which you as a human often use. If someone driving in front of you in the rain or snow, it's changing the lane, you often can, you know, change the lane and then not necessarily looking at the lane markers and everything, right? We used that in some experiments, but the accuracy of our GPS was not good enough to take it on public roads. So we only were there enough to do it on test tracks. In general, of course, there is a lot of potential here, right? I think that what we were after is to kind of show the benefits of this technology in certain applications and not necessarily cover everything with our analysis.
Thank you. And please help me give Professor Orosz a new.